Hey folks, it's Michael with the reasonrxpodcast. Unfortunately, I'm here alone today. Well, as far as co-host, Melanie is busy momming around, Thanksgiving stuff, a lot going on, so she can't join us. Scott Harris is busy too. So you got to suffer with me. Sorry, my ugly mug, my ugly voice, my bad questions. Sorry. So today we're going to be talking to a physicist about physics education, Dr. Hans Schantz. Could you please introduce yourself, Hans?
Hi, pleasure to be on the show with you. It's been a long time since we were both at the
Too
University of
long.
Texas together.
Yeah. But it was a great time. Yeah. Although, it would have been better if I wasn't so sleep deprived and maybe like autistic or whatever. It would have been happier, but still. I did the best I could. But yeah, it was great. So, um, could you tell us a little bit about your credentials? Um,
Sure. I started off in engineering and physics at Purdue for my undergraduate work. Went to the University of Texas where I picked up my PhD in physics. I specialized in electromagnetic theory. In particular, my interest is in how electromagnetics works and how bound or reactive energy somehow decouples away from an antenna and becomes radiation and vice versa. So, that transformation and understanding that physics is what I built my career around. It's had a lot of practical implications. I've worked for the electroscience lab at The Ohio State University. I did ultra-wideband antenna design using those electromagnetic energy flow concepts to try to design and optimize antennas. I developed a location technology called near-field electromagnetic ranging and founded a company called Q-Track with a couple of colleagues and making low-frequency near-field indoor location systems. My company was acquired earlier this year by Geeks and Nerds Corporation, and now I have the official job title of being the principal scientist of Geeks and Nerds,
That's funny.
which
Hilarious.
looks really good on the business card. So
Yeah.
I've got about 40 plus patents to my credit. I wrote a book on ultra wideband antennas, and for fun, my hobby is I write science fiction novels.
Cool. And anything else you want to tell folks about yourself, what you do, and all that, or
Oh, that's pretty much the basics. I've been
cool.
taking my understanding of physics and how electromagnetics works and coming up with practical ways to put it into practice, and along the way developed a deeper understanding of what electromagnetics is, how it behaves, what it does, and how it works.
Cool. All right. So, um, patents, PhD in physics, work in the field. So, if people want authority, it's right there. So today, hope we what we're going to need to do is everyone is going to need to like buckle their seatbelts and check their premises at the door, because we're going to be checking some premises and working on things like that today a little bit. Some stuff might hopefully, I think you'll probably learn a lot. We'll be questioning some physics and the way it's taught, but with good reason and historical background and good epistemology. So some people, okay, we might be stuck on what some physics says. Quantum physics is right. What we learned in school is right. That's the way we do things. But as I say, we need to check our premises at the door. Just because someone says they're a scientist or this is science does not mean it is. We need to judge independently firsthand on our own and not go with that title or word or authority. If we look through history, we see a lot of examples of this. But let's start with one thing I've discussed before. Johns Hopkins, in some graduate program, they have an R3 program where they have to teach their graduates how to do science, how to think, how to be logical. and that's their graduate students, as we talked about. So if they have to teach their graduate students that, are their undergrads learning it, or undergrads around the country? No. Are high school students learning it? No. So we might be memorizing some stuff or learning what other people know about biology and chemistry and physics, but clearly based on what Johns Hopkins is to do, for example, a lot of people are not learning how to do science, how it works, what logic is, how it functions, how reasoning really works. And more. If we look back at the history of science, it's very important to study that so we know what goes on. But let me throw a few examples out now. A lot of people know about Galileo and how he went against authority and what he had to do with, but some people might think that's just an isolated thing. Oh, like science is okay now. But okay, let's take Hans Berger, German physiologist and psychiatrist. He was the first one to record a human EEG, and from what I've read, he was like ridiculed, disregarded. It was thought to be just a little play toy. How can an EEG possibly help us? That's just a little like artifact, just a little toy. No one cares. Okay, look at how the EEG is used nowadays. I think it was Farley Moad, if I remember right, in his book Never Cry Wolf, he discussed at the beginning how stuff he learned by observing wolves firsthand, what was he in Alaska or the Arctic or something, contradicted what he was told about wolves. He said wolves are like this or like that. I don't remember some of the detail. I have to look at the book, sorry. But get the book, read it yourself, learn more about the world, dig into this. He was finding out things about how wolves lived and functioned. It was contrary to what a lot of people said. Or Lynn Margulis, she was the one or one of the ones to discover that mitochondria came from bacteria. And she had to fight like hell to get that accepted. Okay, so, if things are so sciencey and everyone's all good with science, why did these people have to have, why did they have such a hard time breaking in? Why were they rejected? Why were their ideas rejected? Or Semmelweis, who came up with the idea that we need to wash our hands, surgeons need to wash their hands before they go into surgery, ridiculed, I think driven out of his position, not taken seriously at all. These surgeons, what? They're supposed to be educated, but their scientific logical response to him was, we're gentlemen, we don't have germs. Yeah, right. And they're human beings, so don't be telling me that nothing like that happens nowadays either. They were functioning as some humans do. We're social animals. We have all these behaviors. Not everyone is logical. Not everyone is really scientific. Some people are going to reject things like they did. Or Julius Robert Mayer, I think he came up with the idea that heat was a form of energy, and he came up with a more unified theory of energy. And that's part of what he had to do to get this to mechanical, chemical, heat. He saw how they were related, but because he was a physician on a ship, he was ignored. I can put a link in the show notes about that. Dr. Michael Fowler at the University of Virginia, for example, mentions him in this nice article that Fowler has about how to teach heat well. It's called Teaching Heat, the Rise and Fall of the Caloric Theory. But so things are not always as they seem. We really got to look at method and have a good philosophical grounding for logic and science. We can't just think someone uses the word science, so they're talking about the same thing we do. What examples do you have in this regard, Hans, and what do you have to say and add?
Well, it's interesting how, as science evolves, that people who come up with new inductive breakthroughs almost inevitably have those breakthroughs misinterpreted or have to defy the consensus to get their ideas across. I mean, you can look at Wegener's theory of continental drift, which was considered a crackpot notion. You know, how could the rock solid continents be moving around the earth? That's obvious nonsense. You know, even if Brazil does kind of sort of look like it would fit, you know, right snug up against Africa, you know, that's just a remarkable coincidence. And I've seen that time and again in just looking at the history of physics as well. I mean, you know that Newton came into physics at a time when the predominant thinking was the physics of Descartes, that everything was a continuum and a flow of particles that were somehow pushing the planets around the sun. He came up with a mathematical model for understanding all those planetary motions using his theory of universal gravitation, and was able to replicate all of the results that Kepler and his predecessors had come up with. And Newton was a very rigorous thinker, working from the experimental data, deriving his theory of gravity as well as his fundamental laws of motion. But if you go a generation later, people were misinterpreting Newton, claiming that Newtonian physics was a physical model of mathematical point particles that interacted with each other at a distance without any sort of intermediary. Newton held that his laws of motion followed from experience. One of his French advocates, Pierre-Louis de Maupertuis, argued that, on the contrary, you were to deduce Newton's laws from the principle of least action. There's another French mathematical physicist, the Marquis de L'Hopital, who argued that Newton's laws were a priori deductions of pure thought. If you look at Jean-Laurent d'Alembert, he treated Newton and Newtonian physics as an abstract mathematical system. Newton's laws were axioms that were obviously and self-evidently true, and then he argued they were all demonstrable by pure reason, independent of any sort of empirical validation.
That's why the Greeks didn't get it, or the Egyptians. It's obvious, but the Greeks missed it, and the Babylonians missed it, and the Romans missed it.
Oh, absolutely. So, and this is where the electromagnetics starts to come in. So when Coulomb starts to investigate the forces of attraction between charges, he discovers that the force falls off as the inverse square of the distance, just like gravity. So people started developing a theory of electromagnetics, casting it in sort of a Newtonian framework of point particles interacting at a distance with each other. So there was this apprentice bookbinder who taught himself by reading the books, sneaking peeks at the pages he was supposed to be binding. His name was Michael Faraday, and he managed to acquire a good enough education to become a laboratory assistant for a famous chemist named Humphrey Davies, and became a well-known chemist and physicist in his own right.
And isn't he regarded as the greatest experimental physicist of all time?
He certainly has a strong claim to that title. Between the work he did, he developed electrochemistry, which is the science of how batteries work. He developed the law of induction, which explains how changing magnetic fields generate electric currents, and that's the basic physics behind generators and motors.
And that's a different induction than we talked about earlier.
Yes, absolutely.
Yeah.
But the neat thing about it is he was not all that mathematically sophisticated. The mathematical treatments of these action at a distance potentials, he simply couldn't follow. And it didn't make any sense to him that An object over there could be interacting with an object over here without, according to this mathematical law, but without any physical mechanism.
And how do you know this? How do you know he thought that?
You can read his writings, and in particular the writings of Maxwell, who was the disciple of Faraday. And in fact, Maxwell is very succinct and elegant in the way he explains the thinking. But Faraday rebelled against these action at a distance laws. He wanted there to be a process, a mechanism connecting charges and currents over here to charges and currents over there.
Causes.
And he invented the concept of a field. And he used that field concept to derive the laws of induction and establish all of these remarkable physical results. As early as 1832, Faraday had come up with the idea that magnetic influences rippled out from changing currents, and he thought that was the basis of light. And he wrote down all of his analysis so that he could document that he'd had these ideas on this date in 1832, and placed them in a sealed envelope which went in a strongbox at the Royal Institute. That envelope actually wasn't discovered until over 100 years later.
Wow.
And so it wasn't until the 1930s when the secretary of the Royal Institute opened this letter and saw, oh my goodness, Faraday had all these ideas back in the 1830s, in 1832 when he wrote this letter.
Nice.
He had eventually, like 15 years later, discussed all this stuff, but he was on the track decades earlier than anyone ever realized. But in any event, it didn't really make all that much of an impact because it was vague. It was this conceptual aid. It wasn't a real mathematical theory.
Quote unquote, yeah.
Until Maxwell got hold of it and put Faraday's notions into a mathematical form. So he came up with what are now called Maxwell's equations.
Mm-hmm.
Of course, when Maxwell came up with them, they were a very clunky, difficult to understand collection of 20-odd different equations. An unemployed telegrapher who was very interested in understanding how telegraphs worked, by the name of Oliver Heaviside, living in his mother's basement at the time, started studying all of these theories that Maxwell had come up with, and actually rewrote Maxwell's equations in the form that we use today. So,
wow.
What we call Maxwell's equations are actually Heaviside's vastly simplified and streamlined version of Maxwell's theory. Well, Heaviside and some of his contemporaries, like Poynting and Oliver Lodge, and particularly Heinrich Hertz, took these Maxwellian ideas and developed the theory of how electromagnetic energy specifically moves from place to place, how an electric field and a magnetic field acting at right angles to each other drive the flow of energy in the orthogonal direction. And when Hertz discovered radio waves in the 1880s and was able to demonstrate that these radio waves move at the speed of light and behave like light, they reflect, they refract, they can be polarized just like light. Once you account for the difference in wavelength, light having a very, very short wavelength, and the radio waves Hertz was using had wavelengths of about a meter or so. And at that point, people pretty much were convinced that electromagnetic theory had, Faraday's ideas had been verified, that these fields were physically real entities moving from one point to another point, conveying energy from one system to another system. But the problem was there were some really, there was bad philosophy in the culture, particularly in Germany, where people were utterly convinced. Even in the 1890s, you have Mach arguing that there is no such thing as an atom. There are only sensations that we perceive, that we, these sensation and perception bundles that we organize using these concepts, and they have no actual bearing to what's going on in reality. Even Einstein, who was one of the more realist of physicists, accepted the notion that we can only understand reality in a tentative way because it's mediated through our senses.
But Einstein was wrong about something? He was a genius. He's supposed to be like, someone says Einstein said it, so it's supposed to be right. We say Einstein thought this about science and the philosophy of science, so it's right. So are you disagreeing with Einstein?
Well, he certainly did a lot of amazing discoveries, but part of the issue is his discoveries got used, in the same way that, Newton's discoveries got distorted into this worldview of, everything is point particles acting at a distance. When Einstein came up with the theory of relativity, people with bad philosophy jumped on it and said, aha, physics proves everything is relative. Mm-hmm. And as the people doing statistical mechanics were able to develop these statistical rules for how gases behave, people took that and ran with it and said, aha, physics proves that everything is random and acausal, and there are no cause and effect relationships in physics. So when you look at all of the bad philosophic premises that came out of quantum mechanics, you'll discover that all of those bad philosophic premises of reality is inherently acausal and nothing can be known with certainty and so forth, they were all developed in the teens and early 20s, long before quantum mechanics came into view.
And then go back to Immanuel Kant, a lot of influence of Kant in there.
Oh, absolutely. And as quantum mechanics developed, it was developed principally by people like Bohr, who held the point of view that science doesn't tell us what nature is, it only tells us what we can say about nature. And he held the idea of complementarity. He argued that if you have two principles that are in contradiction with each other, well, that is indicative that you have identified a great truth, because you only get a great truth when you have two principles in contradiction.
And that was about, that's what Marx said too, but that was after Marx. Same basic influence though, because for Marx, historical reality was thesis, antithesis, synthesis. He looked at contradictions as being essential. And so proletariat, bourgeois, war, destruction, and then the revolution, and then paradise.
Well, yeah, it's that Hegelian strand in German physics where everything is deductive, and we can understand reality solely through our deductive faculty of intuitively obvious facts.
And then point a couple things out really quickly before we go on. On that point, that goes back to Plato. But if folks dig into it, the deductive thing, to know it's wrong, look at what happened through the course of biology, especially. Plato had certain ideas. No biologist believes Plato anymore because of his theory of forms, about his epistemology about how knowledge works. It's inconsistent with evolution. Aristotle was a good biologist. Evolution is more consistent with what he said. Not exactly, he wasn't right about everything, but more consistent. But this whole idea of looking at ideas divorced from reality has a long historical root that's had bad influences on our culture. I just wanted to put that general idea out there so we know where it comes from. I've talked about it before. We'll talk about it more in the future. Don't want to get into it too much here unless you want to, but I wanted to bring that up while we were here.
Well, it all goes back to Euclidean geometry as being the ultimate model of objective truth, that you have intuitively obvious axioms, and you deductively manipulate them in order to establish your entire system of knowledge about a particular area. And of course, in science, those fundamental axioms are things that are derived inductively by taking a look at the evidence and the experimental results.
So maybe it'd be better to call them principles instead of axioms or something.
Yes, that certainly makes sense. I mean, we tend to denigrate Platonists, but in a way, it's a helpful symbiosis between Aristotelians and Platonists, in that the Aristotelian establishes the basic principles through observation. The Platonist takes them and works out their consequences, and then as flaws begin to appear in that deductive system, the Aristotelian identifies and catalogs those flaws and figures out what new principles and new axioms are needed to move forward.
And right there, you're better than what Kuhn said. The theory of revolutions, Kuhn, jacked up philosophy of science. What you said right there is much better. Thank you.
Well, I mean, the interesting thing, and this is something that I've learned through cold, hard experience. Scientists are human. Mm-hmm. They are not purely rational animals. And in order to convince people of the validity of your ideas, there are not strictly rational but more rhetorical concepts that you have to employ in your argumentation. So you have to appeal to things like people tend to be more persuaded, for better or worse, by non-rational things like, well, everyone else thinks this way, so I'll follow the herd and think that too, or a variety of other persuasive factors. And it's important when you're making a case to keep some of those rhetorical aspects in mind.
Yeah.
And Kuhn does correctly identify some of that sociology of science on how hard it is to get people to abandon the principles that they learned from their professors and have taken for granted. It's very difficult to approach data with the humility that is required to question your premises and come up with truly new ideas.
Yeah, I think he's just trying to connect some things that are right, but because of his philosophy, he gets a lot wrong. Fundamentally, he's wrong, but still, we're fission-fusion animals. We're social, so there's all that aspect going on with science, and that's why some of the stuff happened that I mentioned at the beginning of the podcast, like this episode, the things some people had to deal with. The beauty is in the discoveries these people are making, the achievements they're making. That's what we need to dig in more, not just look at, these people were mean to him. That's something we got to consider, but the really interesting thing, the thing we learn more about how to think and how to be human and how the science works, is like what they did, how they induced things, the cognitive induction you're talking about instead of the electromagnetic induction. Yeah, but
absolutely. And the same thing happened in quantum mechanics. There was a French PhD student named Louis de Broglie who came up with the whole wave theory of quantum mechanics, and Schrodinger took that and developed the Schrodinger equation. And that was very controversial at the time, because Heisenberg had developed these matrix methods where you basically take the goes into and the goes out, and you don't worry about any physical process, and you apply some matrix manipulations and you get the answer coming out. And he did not like the wave approach to things. In the early 1930s, John von Neumann claimed to have proven that the whole de Broglie approach of physical waves guiding photons or particles through quantum mechanical systems. Von Neumann claimed to have proved that it was impossible, and that approach was set aside, and everyone went down the whole Heisenberg, Bohr, Copenhagen theory of quantum mechanics. That was accepted as the dogma.
Mm-hmm.
There's a physicist, John Wheeler, who was the doctoral advisor for Richard Feynman, who actually got another professor named David Bohm to Princeton. David Bohm had worked with Robert Oppenheimer at Berkeley, and he wrote a very well-regarded book on quantum mechanics. But in doing that, he developed doubts about the whole Copenhagen program and approach, and he revived the de Broglie approach. He was able to show how von Neumann was wrong in his disproof, and redeveloped the idea of quantum fields or quantum potentials serving to guide quantum particles. Well, Bohm was suspected of communist leanings and ended up leaving the country. Oppenheimer led a symposium at Princeton on this Bohm-de Broglie pilot wave concept. And according to one of the participants in this seminar, after several hours of arguing and debating Bohm's ideas, Oppenheimer acknowledged that they couldn't prove Bohm was wrong, but Oppenheimer argued, we'll just have to ignore it.
Wow.
And that's largely what the mainstream of physics did with the whole pilot wave theory for the next several decades.
And so we're saying, let's get this straight, wrap our heads around this. So a lot of people think quantum mechanics, the interpretation nowadays that everything's all uncertain and there's no cause, that's been proven. So you're saying it wasn't really proven, it's just accepted socially, kind of like some religion. You got to accept the parts of the religion, and that there was this theory that worked, but it was not assessed and evaluated. It was just dismissed.
It was largely dismissed. And in fact, when I was a graduate student at the University of Texas, I had the great good fortune to have John Wheeler on my own doctoral committee.
Wow.
And I had the opportunity to talk with him, and we'd talk about the history of physics, about his work on the Manhattan Project.
And Oppenheimer was on the Manhattan Project too, right?
Yeah, he was the director
earlier.
Oppenheimer was the director of the Manhattan Project. Well, I was looking back a couple of years ago. I was looking back through my notes and found a conversation that I had forgotten, that I had with Wheeler, and I had asked him about the pilot wave theory, and he scoffed and said, that's the screwdriver theory of quantum mechanics.
What does that mean? Screwdriver theory?
Well, I think he meant that it's an arbitrary theory that's designed to tweak and adjust the parameters to provide a physical model of what's going on to help comfort the reactionary realists in physics who aren't able to accept the concept that everyone else accepts, that things are acausal and you can't really understand the physical processes that are going on.
And so he is more also like pure math rather than having a causal theory?
Well, his idea, in fact, he was an advocate of what he called it from bit, that physical reality is information, and the critical thing is the observer participation in that reality. And we can go into it further, but that's the key part of his thinking.
Mm-hmm.
So after he told me that, I wasn't quite sure what he meant. He was dismissing it. So I asked him, since I knew he was an expert on quantum measurement, I asked him if he had done any sort of an analysis, or if he knew where I could go to take a look at, why is this pilot wave model wrong? Why are you dismissing it? And his answer was, I really ought to look into that someday so I can figure out why it's wrong.
Wow.
He had studied with Bohr. He had accepted the
Wow.
Copenhagen interpretation. In retrospect, I don't think he ever seriously questioned those ideas and considered the possibility that there could be an alternative
And
to
then
them.
it's important to point it out. People might be thinking, well, they're great scientists. What do we have to say? Well, look what Copernicus did to Ptolemy. If Copernicus and others hadn't questioned Ptolemy, where would we be in science and astronomy? Or Kepler. If he hadn't questioned whether circles were actually the way things worked, where would we be? We need
Well,
that questioning.
one thing that's very interesting about physics is how you can have two different mathematical models of a system, both of which give you an exact answer in accordance with the experiment, but have profoundly different physical interpretations. Like in electromagnetics, you can look at electromagnetics using fields like Faraday did, or potentials like a lot of his contemporaries who were into the action and distance approach did. And mathematically, you can get the exact same answer. If you take a look at the field approach, the field approach will tell you that energy is stored in the space around and between charges and currents as they interact.
And so for folks, it's kind of like with gravity too. Like the potential energy thing, if we go up higher on a ledge and jump down, we can make something happen because it's like the stored energy.
Yeah, you can think of it that way.
Or a spring, like a spring, right? Storing energy.
Yeah, if you look at electromagnetics from the potential point of view, it tells you that the energy density is associated with the charge distribution. So it's saying the energy only exists at the location of the charge or the current. So as two charges interact and one loses energy and one gains energy, somehow that energy is being transferred from the one charge and current distribution to the other. And it disappears here and it appears there. Energy conservation is satisfied, but it's a completely different physical picture of how reality works. The field point of view is a picture of a continuous transference, a continuity of the flow of energy from one point to the other as conveyed by fields. The potential point of view says energy is conserved, but it disappears here and it appears over there, and who cares because we're only measuring it over here. If you're measuring it in between, well, then you've just set up another system where the charges and currents there are interacting with the charges and currents in your measuring instrument. And both approaches mathematically will give you the exact same result. There isn't an experiment. Well, there are some very esoteric experiments that purport to distinguish between the two, but it's very difficult to do in classical electromagnetics. Another good and even simpler example is when you look at the physics of wave motion. If you pluck a string and you look at how that string vibrates, there are a couple of physicists who looked at that problem back in the as early as the 1700s, and you had some physicists arguing that it was wave motion, and you could look at the equation for waves propagating back and forth, bouncing back and forth on the string. Or you could look at it with a completely different mathematical model of the string just oscillating up and down. And two completely different models. In the one case, the string is just moving up and down, and that energy isn't moving from place to place. In the other model, it's two waves interfering with each other, bouncing off of each other. It turns out the models are mathematically exactly alike, but for a long, until Fourier was able to demonstrate that, you had, I think it was Euler, the mathematician, who went to his grave convinced that the oscillation people were wrong and it had to be traveling waves.
Wow.
But it turned out that they're both mathematically equivalent. He was convinced they had to be wrong because he knew the one method was right and the other method was obviously had a different physical interpretation.
Mm-hmm.
But this happens in physics all the time, where you have models that are mathematically equivalent but drive different physical interpretations.
Mm-hmm.
So it gets tricky picking between them and trying to figure out which one is the true model that reflects the underlying reality.
Yeah, the causation, nature of the things and all that. Yeah, but interesting. But and some of this, one thing I wanted to point out too, like and we talked about Einstein earlier, just to go back to that, people get things wrong. I'm wrong sometimes, you're wrong sometimes. We shouldn't deify Einstein. He can be wrong in some fundamental principles about some things. We need to look at actually what he did and not just like argue from authority or, as I say, deify him. Look at he's a genius. He did some great things. Can't disagree with that, at least if you want to be honest. But he, like everybody else, could be wrong, and in fact, in some ways, philosophically, he was. So, that's one thing I want to bring up in this episode, drive home a little bit, let people take serious the fact that there's great people out there doing great work in science, but we got to know how science works and know that the important thing is the induction in it, and not believe what someone says just because they call themselves a scientist or they say this is science. We need to know how science works, and it's not some airy-fairy thing in an ivory tower divorced from the world. It's like stuff we can observe around us, and hence, like, some people can come along like Faraday or Newton and do great work, because like Newton was, he grew up on a sheep farm. They were all impoverished, but he was learning a lot about how to think even then. Talked about Abraham Lincoln, the guy who, Browning. I think he was Mormon. He developed he came up with a lot of inventions and has a lot of patents on
the
guns.
gunsmith.
Yeah.
Yes.
Rifles, armaments. He had maybe a 4th grade education, 2nd grade, but he learned when he was young. Someone gave him a rifle that was messed up in many ways, but his dad was like a blacksmith or something, and so he knew some of that. So I don't remember what he was, 9, 12, but he looked at it and was like, oh my gosh, I can't do anything with this rifle, it's horrible. But then he stopped and think, wait, the barrel's bent, but I know how to straighten that. This part over here needs to be replaced, like the spring's broke or whatever he said, and this part needs to be fixed, and this, and hey, then I got a rifle that works. So he learned how to look at the individual pieces and then put them back together, how to analyze and synthesize, going back to, even if he didn't do it intentionally, he was following some of the methods of the Greeks to not just analyze, as people do too much nowadays, but to synthesize and theory build. And when he learned how to do that in principle, and not just for guns, because he applied the same methods to organizing factories to make them more efficient.
Well, it's remarkable how many of the real pioneers in even in electromagnetic physics were largely self-taught. I mentioned Faraday teaching himself physics and math and science by reading the books that he was binding as an apprentice bookbinder. And in fact, he got his first job by attending a lecture that Humphrey Davies gave at the Royal Institute, writing up his notes in a very neat hand, binding the notes together, and then presenting it as a gift to the great Humphrey Davies, by way of an audition to get a job with him as a laboratory assistant. And that's how he got his first break as a professional scientist, becoming a laboratory assistant.
Wow, nice.
Oliver Heaviside, I think, didn't have a formal education beyond elementary school. But after he learned basic reading, writing, and arithmetic, he had the benefit of an uncle who was also a famous electrical engineer named Wheatstone. The Wheatstone Bridge was named after his uncle, who kind of tutored him and got him a position as a telegraph operator. But he was entirely self-taught as a telegraph operator. He went to the library and studied all of the books he could get, came across Maxwell's treatise and read it, was very confused by it, and finally, after he'd kind of sort of gotten the gist of it, got frustrated enough that he went off and started writing his own papers so that he could more or less explain these complicated ideas to himself. And it was very interesting to me. On a trip to England, I visited Newcastle, which is where Heaviside was a telegraph operator, and the library that he visited is still there, and you can actually go and peruse the physics books, and they still have all of the 19th century physics books that Oliver Heaviside was probably pulling out, checking out, and reading to teach himself electromagnetics. And that was a real fun experience, getting to see the books from which Heaviside taught himself electricity and magnetism.
Pretty cool. Did you walk down the row of books and touch all of them with your hand so you know you touched one of the books he touched?
Hoping some of it would rub off on me.
Yeah, no, I did something like that when I was at one of my sisters graduated from the University of Virginia, and I went to her graduation ceremony, and she was picked to stay on the lawn, one of the few students that they picked to do that every year. It's the original part of the university. They call it the lawn. And I'm walking along on the bricks. So you got the dorms. I think they're inside, outside. Some facing each other, some facing outside. She is facing inside. Then I'm walking on these bricks alongside there. The lawn in between the apartment, the rooms facing inside. And I'm thinking, man, Thomas Jefferson stepped here. Wow. It was great. No telling who else stepped on the same brick that I did.
Well, it's so neat cool. Having that connection to history, which is hard to get in this country because our history is so recent. I grew up in Idaho, in Pocatello, Idaho, which was founded in the 1880s, and an ancient building in Pocatello is one that dates to the early 1900s.
Yeah.
So it wasn't until I came back east to go to school that pre-Civil War buildings, I got to see some of that. But you go to a place like England, and one of my most memorable experiences there was in York. I visited the cathedral, and down in the basement of the cathedral, where they were starting to do some excavation to stabilize a tower that was beginning to, the foundations were beginning to settle, back nearly 100 years ago, they excavated and they found the original foundations of the Norman cathedral that was built there about almost 1,000 years ago.
Wow.
And below that were the foundations of the Roman temple that was built there, almost 2,000 years ago. And you could actually see the pavement and the sidewalk that was there when Constantine learned he was the emperor and headed back to Rome. So it was really amazing getting that connection and seeing that continuity with all of these things that you just read about in the history books.
But I guess that's one thing better about living maybe in Texas. So around here in some places, you've got some older archaeological structures. I know one time I had a job in South Texas, and we were going on some private property to do some things. Company had to get permission, all that. But it's right there on the Rio Grande, and we were at a place where it wasn't like flat and then river then flat. It was cliff, and we're driving around doing things on someone's property, and we come to this building. I think it was a fort. It looked like a fort from like the 1500s, 1700s. It was so old, and the size of it, worn down. I don't think it would have even been from 1800s because it seemed so weathered. But so possibly it was like a Spanish fort up on the Rio Grande from the 1500s or something. You know?
Well, they had missions that they built.
Yeah.
I don't know if it was that early, but you know, you can still see the Alamo, of course, and I think there are some others that are well preserved there.
Because like Cabeza de Vaca, Spanish explorer, shipwrecked about 1540 or so. He was a slave of Indians in Texas and Mexico for maybe 3 years or so. Walked like 3,000 or 5,000 miles or something barefoot, basically naked. And then he was trying to seek out some Spanish settlement in maybe western Mexico, I think it was, kind of northern western Mexico. So yeah, you know, there was a little bit then, but a lot more settlement, little more settlement after that probably. 1570s there was a lot more, and then a little bit. Then yeah, 16. When was it? Jamestown? 1607, 1610.
Something like that, yeah.
Yeah. So, but anyway, we're getting a little far afield.
It's interesting how having that historical perspective really helps you understand even something as supposedly modern and up to date as physics, because inevitably what happens is, you know, the professors who write the textbooks kind of copy and paste the stuff from the old textbooks that they found useful and ignore everything else and express, you know, those basic principles and teach them to their students. But you know, the way knowledge grows, there's all kinds of interesting facts that are discovered and then set aside. And I saw that in particular when I was working in ultra-wideband antennas. Because the very first ultra-wideband antennas were invented by Hertz himself. He was doing spark gap impulses. And his contemporary Oliver Lodge invented some very basic broadband antennas, including the Biconical Antenna, which is basically two cones that are fed from the pointy ends of the cone, or a bow tie antenna, which is triangular planar elements that are fed from the tips of the triangles. But as radio technology advanced and people were able to make sine waves instead of spark gap transmissions, they were using narrower bandwidths, and they could get away with just using a thin wire antenna, you know, a single tower or a long horizontal wire to pick up the signals. So radio engineers completely forgot about biconical antennas. In the 1930s, they were rediscovered as frequencies got high enough and bandwidths got broad enough for them to start to be of use again. One famous antenna engineer named Harold Wheeler rediscovered the biconical antenna and immediately filed a patent on it. And the patent examiner, or actually it was his patent attorney, who said, oh no, you can't do that because Oliver Lodge came up with it first. So this guy who was the leading antenna engineer of the period had no idea that Oliver Lodge, who was actually one of the pioneers of radio, had actually already invented that antenna.
Wow.
Another RCA engineer, a guy named Philip Carter, came up with the biconical antenna yet again about 2 years later. His patent attorney wasn't as familiar with the prior art, so they went ahead and they submitted an application to the patent office, and the patent examiner wasn't familiar with it either, so he got the second patent that the patent office granted on the biconical antenna, because no one was aware of that Lodge prior art.
And then that's very go ahead, really, then I'll add.
Well, I was just going to say I can give you a number of other examples, but time and again, what you see, in fact, at least 3 times in the history of ultra-wideband antennas, everything had to be rediscovered. There was the original rediscovery, or the original discovery by people like Hertz and Lodge in the spark gap era. There was another era in around the 1930s where people revisited all these ideas and rediscovered ultra-wideband antennas. But then technology went a little different direction. And when I started in ultra-wideband antennas, there were people who thought that you basically couldn't make an efficient ultra-wideband antenna, that it had to be resistively loaded. And again, all this earlier work had been forgotten. So when I started using my energy flow ideas to invent antennas, I came up with all kinds of different inventions, and then a year later, as I dug deeper into the art, I realized, oh, these had already been done.
Wow.
They weren't in any of my antenna textbooks, but back in the dusty pages of the journals were all of these brilliant ideas that had been overlooked for 50 or 60 years.
Yeah, and it's important. Let me cut in really quickly in teaching, and in developing new ideas and for science to progress, to look into that. Like, where did Copernicus get the idea of a heliocentric system? From Aristarchus. He read ancient Greeks. Galileo, I've seen indications that he was very influenced by Aristotelian methods. Where did William Harvey get the idea for blood circulation in the body pumped by the heart? By reading what Aristotle said about the water cycle. He looked at the heart as being similar to the sun. He got some things like wrong, like these some metaphors and stuff, but there was enough cause-effect situations going on there for him to drive it forward. It was enough of like a green light. So this stuff's important. And then one other point, like Dr. Michael Fowler at the University of Virginia makes, it's very important to study the history of ideas and how things developed, because the mistakes that people made, modern people are probably making too. Just because science has learned science, quote unquote, that, and not to doubt science by quote unquote, I mean just some people, in science is fine, but just because it's known that heat is a form of energy doesn't mean that everyone knows that. And some people on a level developing from a baby to an adult, they can still have some kind of implicit idea of the caloric theory without really knowing it. So the mistakes people made before, these were very intelligent people in the past. They weren't stupid. They were scientists. And so mistakes they made, people nowadays will probably be making too. So you can identify them with them, and then from that, learn what your mistake is, how to do things right, and learn how to think and be logical and do science. There's a lot of lessons we get from that.
I think it's very helpful to look through those lessons and understand the processes that the original discoverers used to come up with their conclusions. For a couple of reasons. I mean, one issue is the history of science is written as this sort of streamlined linear process of discoveries building on discoveries leading right to our present understanding.
Yeah.
Where no one was ever wrong, per se, but they discovered something new and made a step forward, and discovered something new and made a step forward. It's really helpful to look at all of the detours and sidesteps and mistakes that people made along the way that are written out of the science history, because in science, as in war, it's the victor who writes the history books. So having an understanding of things like the caloric theory of heat, or in my case, the action at instantaneous action at a distance theories of electricity and magnetism, are helpful in trying to understand how we got where we are, and what we can do to push it further.
And how to evaluate science, and knowing that scientists aren't omniscient, they're not gods. It's they're human beings. They make mistakes.
They are profoundly influenced by the society and culture in which they live and
Yeah.
tend to adopt the prevailing philosophic ideas as a filter through which they interpret their physical results.
Yeah.
And
It's like,
if you are sufficiently broadly read that you can step back, step outside of that contemporary filter and be able to approach science from a wider variety of models and perspectives, that's just, you know, more tools that you have in your intellectual toolbox to be able to understand and evaluate what's going on. You know, there's this story that Richard Feynman likes to tell about
he's great.
how, you know, the story about integrating or you know, differentiating inside the integral before you evaluate it, or I'm trying to remember the exact trick. It's a calculus trick that's a little bit obscure that he knew how to do and do really well. And what would happen is his friends, his fellow grad students, even his professors would run into a calculus problem that they couldn't solve. And they'd use all of the you know, complicated, sophisticated, tricky methods, you know, contour integration and things like that, using complex variables, you know, infinite series and so forth. And when they couldn't solve it, they'd bring it to him, and he'd use his simple trick, and he'd get the answer.
Wow.
But his simple trick, people didn't generally appreciate. But because he had that, because they'd tried everything else except his simple trick, a lot of the times he was able to solve problems. So when you have these unconventional methods or models that aren't widely known, it really helps you be creative in a way that people who are locked into conventional thinking aren't able to match.
Yeah. And we're social animals, so the social thing is great. We should be. We have to be. It's our nature. You pick things up from the culture. We're finite and limited. We can't do everything. But we got to remember the fission part of being a rational animal, a human being. The fusion part, fusion, social, fission. We're a social animal that says, don't tell me what to do, and we think independently. We got to make sure, for our own sake and for the sake of the culture, those we live in, you know, I mean, those we love, our friends and family, that we think independently. We got to have that historical background, that creativity, make sure what people are doing is correct, and like correct the social mistakes, or like some fads, we don't want to be a fad, like a fad in physics or in politics. If it's clothing, hairstyle, big deal. We need some of that for like social cohesion and stuff like that. It's our nature, but it shouldn't be in everything.
Well, you have to have a broad enough background in the history and philosophy of your field to be able to step back, look objectively at today's trends and, you know, today's fancies, and be able to think outside of them and objectively question your premises.
Yeah, so go back and look at quantum mechanics, Einstein, other people, see if they're right, respect what they did, correct what they didn't do right. But we got to do that with Einstein, just as we did with some Kepler and some Copernicus and some even more Ptolemy. But I think, was it Kepler, was he like the first scientist to, I don't know if you're like have dug into the history of science this much. I know you've done a lot, clearly, but was he the first one to write down pretty much everything he did in his successes and failures as well? Kind of one of the first ones to start writing down experiments instead of just recording results, as Galileo and Newton. Galileo did some more. Well,
I know Kepler. You know, Kepler started off trying to model the solar system using this
yeah.
this Platonic solid model where I forget exactly how it worked. Like there's a tetrahedron, within Mercury's orbit, and a cube, and a octahedron, and and so forth.
All the
He had
platonic solids. Yeah.
this ratio of nested platonic solids that was his a priori hypothesis for how the orbits behaved. But he was enough of a scientist to be able to take a look at that and say, this just doesn't work, and you'll be able to realize that the orbits can best be modeled as ellipses.
Mm-hmm.
What's really fascinating, if you want to do a historical what if, is to realize Archimedes did a lot of the work on the geometry of conic sections that was subsequently lost. And it's that geometry of conic sections that's the true geometry of basic kinematics. You have your parabolic motion. If you go back and take a look at early medieval ballistics manuals, you'll see that they assumed a cannonball was fired in a straight line, straight out of that cannon, until it got far enough away from the pernicious terrestrial influence of the Earth to reach the heavens. Then once it got into the heavens, it followed a circular arc, because that's what heavenly motions do, until it got down close enough again to the Earth, whereupon it followed a linear trajectory to its destination.
And I think I've heard, like in that, sometimes some people would think back then that you'd fire a cannon, it would go in a straight line, and then all of a sudden it falls straight down.
Well, that's part of that same model of taking Aristotelian physics as your sole guide to motion, and all motion must be lines and circles.
And speaking of the historical thing and people doing it today, some people, for a fact, think that. I know someone who I tutored who sold handguns, and he was at a show, and someone told him that's what a bullet did. It went a straight line, it ran out of energy, and then it fell straight down. He believed that nowadays.
Well, in a way, with fiction, that's not that far off, because it'll tend to follow the straight line trajectory, but then as it slows down, of course, it's still falling at the speed of gravity one way or the other, but it wouldn't be a pure parabolic trajectory in that case. If you threw in resistance.
But the way this guy did it, it was like a rectangle.
Yeah, that's not right.
My friend was trying to talk to him, but just got sick of it because the guy was he's not so stupid he couldn't get anything. It was just driving him crazy. I can't take this. But, so sorry, what were you saying? You were talking about,
Well, I was talking about how a wonderful historical what if is to speculate what would have happened if the geometry of conic sections hadn't been lost.
Mm-hmm.
Because if that had been available to medieval scholars and they'd started trying to fit things to parabolas and ellipses earlier, we could have had the science of mechanics hundreds of years earlier.
Oh, yeah. And then that was available to Galileo and Newton. They studied it like the geometry we do. We think it's tough. Back then, they really studied geometry, Euclid's Elements.
I have tried reading Newton's Principia, and it is amazingly tedious. It's actually all kind of sophisticated Euclidean geometry.
Mm-hmm.
In principle, you ought to be able to follow it, but the constructions he did were just so amazingly intricate and frankly confusing that it's very tough to read and very tough to follow.
That's an interesting thing about how we function as animals, how our minds and brains work. So I think Newton and some people at his time probably had that stuff so well integrated because they were taught it, trained well in it. It'd be easier. Whereas a lot of people nowadays who give limited geometry, you really have to study geometry really well and all the conics to make that go smoother. I've heard that, I think even Richard Feynman said the same thing. He said he tried to study it but gave up trying to study the Principia.
There are some sections of it that are well worth reading. Like
Yeah.
I'd highly recommend his Rules for Reasoning in Physics.
What are they? Do you recall?
I remember the one that most impressed me was, to the same end results ascribe the same actions. So if you have, basically don't come up with multiple hypotheses to explain similar results. Try to unite them under a single explanation.
Want me to read them? I just looked them up.
Oh, sure.
I got the rules right here. Okay.
Oh, you're cheating. You're looking stuff up.
Yeah, I asked Dr. Google. Dr. Google. Okay, Newton's Principia, Rules of Reasoning and Natural Philosophy, translator A. Motta, M-O-T-T-E. Do you know how to pronounce that? Is that right, Motta?
Maybe Mott.
Mott?
I'm not sure.
Okay, that sounds better, yeah. 1729. Rule 1. We are to admit no more... And listen to this. People say Newton rejected causation and was about math. Okay, now listen to this, folks. I heard that. My physics teacher in high school said Newton was the one that showed you use mathematical description, causation doesn't matter. A physics teacher said that. I didn't listen too much, but okay. Rule 1 of the guy who supposedly is about math and not causation. We are to admit no more causes of natural things than such as are both true and sufficient to explain their appearances. And then a little note, to this purpose the philosophers say that nature does nothing in vain, and more is in vain when less will serve, for nature is pleased with simplicity, and affects not the pomp of superfluous causes. Rule 2, therefore, kind of what you're saying, therefore to the same natural effects we must, as far as possible, assign the same causes. It's to respiration in a man and a beast. A human being, other animals, respiration is respiration. The descent of stones in Europe and America, fall is the same fall no matter where you are. The light of our culinary fire in the sun, there's where he was wrong though. A fire in the sun, well, it depends what he means, of course. Light is light, but a different cause. But then he's talking about causes, so I think he's saying here that because they didn't know about radiation, that a fire in your fireplace and the sun had the same cause. The reflection of light in the earth and in the planets, same causes for things like that. Rule 3, the qualities of bodies, which admit neither intention nor remission of degrees. I'm not going to go into an explanation of what he all means by that. And which are found to belong to all bodies within the reach of our experiments, are to be esteemed the universal qualities of all bodies whatsoever. And then I'm not going to read the little description, well, maybe a little bit there. But no, there's a longer paragraph here, a few paragraphs, and he's talking about hardness and gravity and I think and some things. Rule 4, maybe I'll put this in show notes and people can read that part on their own.
It's well worth reading because you can see very clearly he had a very rational approach to understanding it, and in effect, it's I don't think he acknowledged it, but he's effectively following. Was it Wilhelm of Occam? Occam's razor?
Oh yeah. Occam's razor. I don't remember about the first name, but yeah. You want to ask Dr. Google while I read Rule 4?
You can ask Dr. Google.
Okay. I'm not talking to Dr. Google anymore. Okay, Rule 4. In experimental philosophy, we are to look upon propositions collected by general induction from phenomena as accurately or very nearly true, notwithstanding any contrary hypothesis that may be imagined, till such time as other phenomena occur by which they may either be made more accurate or liable to exceptions. So in that, I understand that now better than I ever could have when I first read this when I was a punk kid, because it's just so abstract and takes more logic, epistemology, and philosophy. But and so basically he's talking about something like, I think some people, this is I think one thing my physics teacher said, maybe he learned it from someone else and he was just mouthing off without understanding, but because clearly Newton talks about causation at first, but like my physics teacher said that I think he used the word hypothesis, And what Newton means here when he says, notwithstanding any contrary hypotheses that may be imagined, he's talking about Descartes, I think, and making crap up, which is pseudoscience. He's saying that if you induce some causal connection, or the nature of something from experiment, then it's true. Even if someone makes up some nonsense to the contrary in their imaginations, and you look at it as being within the context of the concrete things you're inducing from, and maybe you can expand it a little bit more until you find there's a new phenomenon that comes into play, just as Newton came up with his theory, some of his theories of motion by looking at things that only went a certain speed. And so people had to figure out that, oh, when things go faster than this, whoa, there's the liable to exception part that he's talking about.
Well, it's fascinating when you study relativity. People like Heaviside and George Francis Fitzgerald and Lorentz and Poincaré were developing the math necessary to understand what happens to electromagnetically bound objects as they begin to approach the speed of light. That's why we call it the Lorentz-Fitzgerald contraction. That was then calculated or you could deduce from special relativity.
And what exactly is the contraction? How would you describe it?
The idea is that there is a contraction that goes as the square root of 1 minus the ratio of the velocity to the speed of light, that quantity squared.
But is it like the length of something in the direction of motion?
The length in the direction of the motion gets shorter.
So like if I'm driving, and I actually did this when I was in that physics class, I drew this little, I wish I would have saved a picture. I drew a diagram of like a car going about the speed of light and another car was like shorter. So the idea is like if we're driving northbound on a road and there's a car going southbound, the car that's southbound will appear shorter to us than it will if we're stationary, right? If we're going like really, 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 really fast.
Yeah, you'd have to go really, really, really. You need a few more reallys there. But yes.
Sorry. Really? Is this right? Really, 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 really fast? Is that better?
Yeah, you're getting close to enough. But...
Okay. So in other words, you got to go about, what, 98, 99% of the speed of light?
Well, to see a real significant contraction.
Yeah. But anyway, so you're talking about the Lorentz contraction. I wanted to clarify.
Yeah, but all that stuff was being developed organically from the laws of electromagnetics, and what Einstein did was effectively invert the hierarchy. He came up in special relativity with two principles: the idea of observer independence, that the no observer has a preferred frame of reference, so all experiments in any inertial frame of reference will give you the same answer. That was kind of a reaction to the whole Michelson interferometer experiment, where people were trying to measure the ether drift with an interferometer and discovered that they couldn't see any change in the velocity of light no matter which way they spun their interferometer around. And then the other principle is that the speed of light is an absolute limit, and that all signals and information has to travel at the speed of light. And from those two principles, you can derive special relativity and all of these things like the length contraction that had already been established by other investigators. And what's kind of interesting is physicists have already demonstrated that one of Einstein's axioms of special relativity is wrong, because we've been able to measure an absolute velocity with respect to the background radiation of the Big Bang. And our galaxy is moving a couple hundred kilometers per second with respect to that background radiation. So there is an experiment that you can do anywhere in the universe and measure what is your velocity with respect to that, in effect, preferred inertial frame, the rest frame of the background radiation from the Big Bang.
Wow, interesting. Yeah. But let's see, we've been going for a while, and I need to get some dinner in my body. My brain is starting to feel it a little bit. But
well, I'll be happy to come back another time.
Sweet. Amen. I'm glad.
Talk Good. About more things. Yeah, I'm writing a book on fields and energy that will help introduce. The subtitle of it is How Electromagnetics Works, and the goal of the book is to try to explain in relatively simple and straightforward methods, using a lot of diagrams and geometry of fields, how electromagnetics works and how it carries energy, how fields carry energy from point to point.
Cool.
So I'll be looking forward to coming back again sometime and discussing that with you, and I'm sure there's a lot of other things that we could discuss.
Yeah, it'd be nice to unpack some of this more, because it might have been, for some folks it'll be fine, bam, 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 but for some, all the names and ideas might have been a little technical. So might be good to unpack some of this if we could. And then hopefully, we got good discussion here. Had to start out disabusing some people of what they might be thinking about science and all that, to let them know that, hey, we can't just trust someone because they're called a scientist, or someone says this is science. We got to dig into things, and we can each learn the ideas and methods we need to evaluate within certain parameters what is science and what is not. We can't, sometimes it does take highly technical knowledge, like when they're doing something in biochemistry. Is this a proper marker for measuring some aspect of the body, and is this machine the right thing to measure that? And we don't know. I don't know how some of these machines work, but still, we can, when we learn about how science works, how to build a theory, how to assess some evidence, we can get a general idea of what's going on and whether something's valid or not. Any like to elaborate on that a little bit, or close up for folks?
No, that's a good summary. We had a very broad-ranging discussion. Everything from the goodness, we went from Aristotle and Plato and Aristarchus all the way to modern times and quantum mechanics. And but I think that it is important to understand the methods of physics and how physicists in particular and scientists in general reach their conclusions about things. It's important to take a look at the history of how those principles were reached, to understand the methods and the evidence that gave rise to those conclusions. Too often, the conclusions are, prepackaged, shrink-wrapped, and served up in class without enough of a discussion of where those ideas came from. I think it's partly a reaction to trying to cram too much material into too little time.
Yeah.
So you just kind of take a look at the conclusions and summarize what the answer was without going into any detail on where that answer came from. So you can see how that happens and why that happens. But to have a good, solid education, you do need to have that methodological and historical and philosophic background on the subject.
And then, so if folks aren't maybe making the connection quite yet, the society we live in, you can't get around having to deal with science. It's everywhere, 24/7 in all you do and everything you read. So you need some like scientific knowledge and understanding, scientific literacy. Otherwise, you know, you just got to go out in the woods and live alone or something. But once you're in this culture, you got to deal with it. So we should have the tools to. And then some of what you're learning in physics and chemistry is not purely physics and chemistry, but some of the methods we learn can be used in other areas of life, at work, child rearing. So when you're learning physics, oh, well, I'm never going to be a physicist when I get older. Well, you are going to have to deal with science and the culture, as I said. You are going to deal with cars. And if you learn how to assess evidence, how to put theories together, then you have methods you can use in any career.
Oh, absolutely.
So, because no matter what you're doing, you got to form conclusions, convince other people of something, marketing, sales, computer design, whatever. You got to know the context of the things you're dealing with, how to put evidence together, how to form a valid conclusion. So you're spending, for example, $10 million on an advertising campaign that'll be successful instead of a waste of $10 million. So, yeah. So, thank you, Hans. It was great. Enjoyable discussion. A lot of stuff there for folks to digest.
Oh, you're certainly welcome, and I will be happy to come back again sometime.
Amen. See you tomorrow. All right. So, I hope you enjoyed it, folks. If you have any questions, let us know, and we will talk to you all soon. Thanks, folks.